Let's discuss the goodness of fit test. So a multinomial experiment is a probability experiment consisting of a fixed number of independent trials in which there are more than two possible outcomes for each trial, unlike the binomial experiment, which we know bi is referring to two and only produces successes and failures. The probability for each outcome is fixed, and each outcome is classified into categories. Let's consider a tax preparation company that wants to determine the proportion of people who use different methods to prepare their taxes. It wants to test a previous retail trade association's claim concerning the distribution of these proportions. It can compare the distribution of the proportions obtained in the multinomial experiment with the previous survey's specified distribution. To do this, we'll use a chi-square goodness of fit test. Now, this looks like it's spelled chi and should be pronounced chi, but that's a mispronunciation of the word. It is chi-square goodness of fit. So chi-square goodness of fit tests used to test whether a frequency distribution fits an expected distribution. The null hypothesis states that the frequency distribution fits an expected. And the alternative is going to state the opposite, that it does not fit the expected distribution. If we take a look at this data, this is what is expected. So what this is saying is that if we are looking at the people preparing their taxes, we would expect 24% of people to be using an accountant, 20% of people to be doing it out by hand, 35% using some computer software like TurboTax, 6% uses their friends and family, and 15% using a tax preparation service. To test this claim, we'd set the null hypothesis to be that the distribution does fit the expected. So we are saying that it is true that 24% use accountants, 20 by hand, and so on. The alternative hypothesis states that this does not fit. In fact, when we did the observations, we found that the expected distribution is not the same. If we were doing this out by hand, the observed frequency O would be labeled O, and the expected frequency would be labeled E. Now, for our purposes, we'll be using our Rguroo, so we do not need to calculate this stuff out by hand. Although I did leave a slide in here to show you how it's done to enhance your understanding of what's happening. So let's say that we conduct our multinomial experiment by collecting 300 randomly selected adults and asking them how they prepare their taxes. The chart over here states that out of the 300, we found 63 of those 300 using an accountant, 40 are doing it out by hand, 115 are using a computer software, 29 for friends and family, and 53 go to a tax preparation service. Now, if we wanted to see how to do this out by hand, in order to deepen our knowledge of understanding between observed and expected, the observed again comes from the multinomial experiment. The expected is calculated by taking the sample size from the experiment and multiplying it by the probability from the expected distribution. So what this says is that when we conducted the experiment, 63 out of 300 people stated they use an accountant. Our expected frequency for the 300 people would have been 72 when we multiplied 300 by the 24% that we claimed. Let's now head over to our Rguroo in order to see how to perform the chi-squared test by using our statistical software. So we can import a data set if we want or create one, but it's not necessary. The chi-squared goodness of fit test calculator allows us to input this stuff manually. And since you're going to have to create either an Excel file or a data set within our Rguroo, it's the same number of typing. Unless you were using that data set more than once, that would make sense to create an actual data set. So we're going to analytics, then to analysis, and then to goodness of fit. So I don't have it as a data set. I have to fill in this area here. Now, in my table, I have 5 different categories. So I'm going to come here to the plus sign and add 5 rows. Now, the level and the label are the same. So my first one is accountant. Don't ask why they have two spots for this. Second one is by hand. Third one is computer software. The fourth one is friends and family. My labels, I'm just going to make abbreviations. The last one is a tax preparation service. The observed counts were given in the chart. So remember, observed is from the experiment itself. I'm copying those right out of the chart from the PowerPoint. And the probabilities are coming from the expected distribution. You can enter these in many different ways. So you can enter these using the percents. But if you do that, you need to make sure that you're consistent, that everything typed in here is typed as the percent form. Or you can do the decimal form if you prefer. If you leave it blank, it will assume that they are equally likely to occur, and it would calculate it as a uniform probability. Now, it's simple as clicking the chi-square box. For this particular example, I didn't get that far down in the example, or maybe I did and I didn't read it out loud, but we are using a 1.01 significance level, and we use our little eyeball. So now I can see the observed counts that I typed, that Rguroo has calculated the expected, which are the same that you saw in the PowerPoint when done out by hand. We come down here, we can see the test statistic, which is the chi-square test statistic, is 16.8885. And the p-value is very, very small. Now we can do both critical values and p-values. The critical value isn't in this chart, but it is below in one of these graphs I'll show you in a moment. This p-value is very small, smaller than 1%, and therefore we would be rejecting the null hypothesis, leaving us to believe that the actual distribution is not the same as the expected. If you need the critical value, it's here in this bottom chart, it's 13.27. A chi-squared distribution is always a right skewed. And we can see that the observed chi-square statistic, 16.88, does fall in the rejection region, as this is 13.27. Let's head back to the PowerPoint for our next example. Okay, so two things that we do need to check for the chi-squared test, which I probably should have mentioned first. The observed frequencies must be obtained from a random sample. That we should be familiar with, as that is always the case. The other thing we need to check is that the expected frequencies are greater than or equal to 5, which is met if we look back at the chart. All of these are greater than or equal to 5. This is the formula for the chi-square statistic, which again, you don't need to do out by hand. As you just saw, Rguroo does that for us. And we did this at a 0.01 significance level. Again, those are our null and our alternative. And here we have the conclusion, which we'd already concluded in our Rguroo, that we are rejecting the claim that the distribution of tax preparation methods and the expected distribution are the same. That's what we're rejecting. So we're stating they are not the same. Let's try another one. A researcher claims that the number of different colored candies in a bag of dark chocolate M&Ms is uniformly distributed. To test this claim, you randomly select a bag that contains 500 M&Ms. The results are shown in the table, and we'll use a 10% or a 0.1 alpha level this time in performing our chi-squared goodness of fit test. Now, keywords in here is that uniformly distributed is the expected value, which means that these are going to have the same probability throughout, which you see that there are 6 categories, so there's a 1 out of 6 chance for each according to the expected distribution. This is the observed frequency, as those are the counts from the bag of M&Ms. Now let's do our test. Our test is our test are conditions. So was this taken from a random sample? Although it doesn't use the words randomly, oh, it does. Randomly selected bag, so check. And we need to make sure that our expected values are all greater than or equal to 5. But we can check that after we actually run the Rguroo test so that we don't have to do the calculations out by hand. We set the null in the alternative, the null being the expected distribution of the different colored candies in a bag of dark chocolate M&Ms are uniform. And our alternative is that they are not. So heading back to our Rguroo to wrap this up, let's open a new goodness of fit test. We have 6 levels this time, or 6 categories. There were 6 colors in the data set. And let's enter what we know. So we have the first one is brown. The second one is yellow. We have red. We have blue. And we have orange. Oh, wait, we have more. Orange and green. The observed counts from the bag of 500 M&Ms. There was a count of 80 brown, 95 yellow, 88 red, 83 blue, 76 orange, and 78 green. The probabilities, remember, are uniform. So we have choices. We can type in a fraction, 1 divided by 6. In this area, it actually does calculate the division. We can type in the decimal. We can type in the percentage. Or if we leave it blank, Rguroo does default to a uniform distribution. So I'm going to click chi-square. I'm going to change our significance level to the 0.1 and hit our little eyeball. We have our expected counts. The 83.33 come from taking 500 and multiplying it by 1/6. And all of them are greater than or equal to 5, so we meet that last condition we were waiting to make sure worked. We have our chi-square statistic is 3.02, and our p-value is really freaking big, which means we'll fail to reject the null hypothesis. And that means that we do expect that the proportion of the colors in any given bag is uniform. If we need that critical value, we come down here and we'll see that the critical value is 9.2, but the observed value is 3, and we can see it does not fall in the rejection region. And that's how you perform a goodness of fit test.